Okay, this is really exciting. I started Mudfossil University to basically open up science to everyone that didn't understand the rocks that they were seeing, didn't understand that we have new species that they just consider these rocks. They just consider that a rock, which is a goose. And the feather pattern is still in here. I discovered this over 10 years ago. I did all the research on it. And then I also discovered that light and particles are not what they considered them to be. And they still don't understand the light and wave particle duality. And protons are not made of one big ball like that you can smash into little bitty pieces. They're made of a ball of electrons, which are dipoles. That means they have a positive and a negative. This young man that has graduated high school at 9 years old will be able to understand these things. And it's time that we intervene early and get them into this discussion. Now listen to this.
For one Bucks County boy, his graduation is making history. 9-year-old David Balagoon received his diploma from Reach Cyber Charter School in Harrisburg after taking classes remotely. He loves science and computer programming and credits a number of his favorite teachers for his success. While David's parents both have advanced degrees, they say raising a young son with extraordinary intellectual gifts is challenging.
Like, he's a 9-year-old with a brain that just have the capacity to understand and comprehend a lot of concept that's beyond his years and sometimes beyond my understanding.
I want to be an astrophysicist, and I wanted to study black holes and supernova.
Okay, he sounds like he's got a very fertile mind, and he needs to be exposed to some of the things that he was not going to get exposed to in a standard high school or even in any university at the moment. Let me start by talking about his interest, which is black holes. Okay, before we get deep, I just want you to see this is the particles that CERN and Fermilab have seen, which is the black and the glowy part. This never changes. This one can get big and small. And we found them in light. Now they found them as debris from a head-on collision of gigantic particles, hundreds of billions of particles at a time. And all they see is debris, and they have found them, but they didn't realize that they are what constitutes light. The glowy part is here. It can get big, it can get small. The black never changes. You see the black balls here? This is the same picture as this, only this shows the energetic values. You see them here, they look similar. But this one is more glowy than that, you see it? And that's because it's going through the air this way. And this one is concussing with the particles in the gases that are in front of it. The white particles push away, the black particles attract. And it's called dipole electron flood theory. And this is Fermilab's, and I will show you their article in a second. And we actually discovered that we could break these particles apart. When they came in as a complete particle. Two this way and two that way, just like two bar magnets. And really there's one big field around it, so when it bounces back at you. That's why we see light bounce back. It's because it's got like a rubber ball on it. Boing, boing, it bounces back at you. It depends on how fast it's going, first of all, and what exactly it's interacting with. The harder the surface that it bounces off of, the brighter the light, the more blue. The bouncier, the real soft, if it hits it, you get down in the red, and it may not even bounce back at all, and it's going to be black. So this is what we've discovered. We could actually separate the black portion from the white. Exactly what CERN has seen happen, but they didn't realize it was light that they were dealing with, not protons. They were breaking it down to the smallest pieces, but the smallest pieces are light. And we broke the black away, which is the muon, away from the electron neutrino, which is up here. This is the muon neutrino, electron neutrino, muon neutrino, electron neutrino. When we hit that venturi, pew, only the white could squirt through. The black was bounced back. And here it is down below, quite obvious as you can see. The light accelerated due to the Venturi effect, and it's quite well understood. And we funneled that light down like this, so that the white can't get out. The black just keeps banging it and banging it and banging it and squirting it out the other side. Complete separation. This is called fission. When your black separates from the white, it's fission. This is the electron showers. And then this over here is fusion, where the black comes back to the white. And we can just squirt that through that venturi all day long. It's not like a ba-boom and it stops, ba-boom and it stops. It's just squirting the white, separating it out from the black. Now, can we use the black? Can we use the white? I think we might be able to use both of them. We're certainly going to be able to, this is what they would have to consider increased energetic value. Anytime you increase the luminosity, which this is just a luminosity on steroids, when you do this, you increase the energy value. Now, this is that white shower coming through there. They said the muons separate from the electron showers. This is the electron shower. That's all it is the white part of that particle, and then it reattaches here. This is the reattachment. This is fusion. That's fusion. And they make the Higgs fields. Fission was when that broke apart from the white particles. Alright, so here's the fission. And the other part is where we just saw all these fields coming back together. That's the fusion. So we got a lot to look at. Now, we did it with a single particle. We did it with just basically a single wave of light. And the particle accelerated, it split. There's coming at us, these are the fields. These are the actual particles. And we've seen them in red, blue, and green. And the blue, you can see right here, it can accelerate and slow down. They can all accelerate and slow down, but the blue is quite obvious. It's coming in really hot, and then it slows down here and opens up. The red is a much slower impact value than the blue and the green. And I think I've also shown that. I might have it here somewhere. No, I can show it to you. So what I am telling you and showing you and explaining is that these are the particles that make up light. The black, we have seen, no question, separates from the white. Zero question about that. These are the neutrinos. And you see they're different flavors. They call them different. This has two blacks and a white. This one has two whites and a black. This one has two blacks and two whites, which is a photon. Once they get to this phase, that's a light photon. Here it's an accelerated particle, or it's pushing against another particle. So it's losing value or it's gaining value, one or the other. This one is what you would consider a photon of light. It's just pushing everybody out of the way as it goes forward. It's not accelerated. It's just a normal flow of light. These came in so hot that they change their values as they go, and that's what they say. They change values as they go. That's what they call it, flavors. Okay, I gotta be honest with you, Sabine. I think you missed it again. Because as she says, I've tried to figure out why I misunderstood this for so long, and I think what threw me off is
try to figure out why I misunderstood this for so long, and I think what threw me off is all those arrows for infrared light that...
Alright, really what she's missing here is the extreme temperatures out here in the scrub between the non-vacuum of space. It's just saturated with particles, and so is our outer atmosphere. Over 4,000 degrees. That's radiating downwards. And the gravity of the Earth pulls those electrons, which I showed you. Those electrons are particles, or I will show you right now, they are particles coming from the sun. Okay, so I am hoping we are going to have some young minds looking into this, because the sun and all stars and all luminous light-emitting bodies emit particles of light. They're not nothing, they're particles. And I was originally going to call it vortex particle theory. Now I'm calling it dipole electron flood theory, because electrons are dipoles. They have a positive and they have a negative, and they can separate, which I have shown you or will show you. they also have a mass, and it's 0.0005485 atomic mass units. So that means when that light comes in and it gets trapped in our Earth's atmosphere, it's adding weight. So I actually figured this out. The average is 1,360 watts per square meter, and we've got 1,000,000 times 510 million square meters on Earth. I came up with some crazy formula to figure out how much additional weight, literally, the Earth is picking up from these electrons. Now, some of them are going to blow back into space. They're going to just squirt off, and we're going to see it as light from space, yes. But the vast majority are going to be held on the Earth. And that just increased the weight of the Earth. There's no other way to happen. Because every one of these particles. So I said light is dark energy because it has the black side and it has the white side. Alright, it's just like this. In space, if they were together, an electron looks just like that. One side is just dark matter, does nothing more than it's dark energy and dark matter. And this side is the glowy one. It hits something, it bounces. They push away from each other. This is an attractor. That's all it does is attract the white. That's its energetic value, is an attraction value. This is a pusher. This attracts, this pushes. And I've shown this in great deal. You see it again now too. And as that particle comes through space, there's other particles in space. It's called quantum foam. I will show you that as well. And which is other particles in space. They have to push through those particles. Because some of them are going this way, some of them are going that way, some of them are, and they have to come through. So that slows the light down. Alright? The further it is away from us, the more it will slow down because the more stuff it has to go through. As they say in Fermilab, the space isn't empty. It's completely packed with what they call quantum foam. So we have to take a whole new approach at looking at the particles in space. Dark energy and dark matter is nothing more than light until it impacts. This was my, can you see that up there? Light is dark energy until it hits matter and bounces. And I did this, it was 6 years ago. This was 2016. And I tried to interact with Fermilab and all of them to show them our particle stuff. And let me show you that right now. And I was rebuffed, and still am rebuffed. And it's become more and more apparent that it's quite obviously true. You see, these are the flavors of the red. They come in here, you got two blacks and a white in the middle, and then they go sideways, right? And then they go into the photon phase, and then they, just before they go through the Venturi, they just go into insanity land. And then they break apart, white breaks apart from the black and gets extremely glowy. Here, they just say, each one of these is a pulse. So it's boom, 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 boom. This is literally from a construction laser, which they send out pulses of light, and they reflect back, and there's another receiver there. We don't care about that, but that receives how far away the light is. So it measures the distance. These are the pulses. And we see them as particles. And we also see them as waves. Okay, I want you to look at this carefully because this explains everything very quickly. Each one of those waves is one of these particles. Let's go with that. Boom, 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 boom. Again, construction laser. These are calculated pulsations, a certain speed, a certain pulse, and it's very, very quick. And these are the photons of light. The reason this one is big bubbled in the front here is because it is the one that's concussing with all of these particles in front of it. Because all of these have fields as well. So as this field comes forward, creating the field in front of it, all right, that starts to swell up. It starts to absorb that energy. When it gets so full, it flips to the back. The front one, the bottom one comes forward. And then that starts to absorb the energy. I will show you or have shown you. Now, this is going forward, and these are all got to get out of the way. And this just has to keep going because it's getting pulsed and slapped forward. All right, now that particle, if you can see where that particle was, that is a hell of a lot of energy right where that particle was. All right, and then the rest plows forward through it. Now, the reason there's so much energy right now is because it's just starting to accelerate, and then we will see the wave actually leave, the particle actually leave the wave. This is particle-wave duality, and here it is right here. That's it happening. Before, it was just coming through here like this, and we saw it getting really glowy in the front. Now it's starting to stretch out and pull itself right out of the magnetic field. So that is exceeding the speed of light, which is not supposed to happen. This is the actual particle, and this is where the black and the white separate, and there's where they come back together. The venturi is here, which is nothing more than a funnel that forces the light to crush into each other's fields. We're doing the same thing CERN is, except they're hitting them head on. In Fermilab, they're just smashing big, huge particles like this. Let me show you something. They're taking big globs of matter and smashing them together, and they're seeing all these particles that we see, but they're just seeing them in a huge pile of debris. We're actually seeing the particles as you have seen yourself. All right, we can see the particles. There's no mystery to the stuff I'm showing you. And this is what they see at CERN. This is the kind of stuff they see. And then they dig through and they say, ooh, look at that little red one. Ooh, look at this little blue one. And we actually see the actual particles. And that's done with CMOS in a smartphone. And we can do it with CMOS because we're not damaging the CMOS like they would. They're using protons. When they smash something together, it's like hitting tractor-trailer trucks together. And of course they're going to damage any CMOS thin film. It'll smash it, it'll destroy it, yes. So they use other magnetic interactions which destroy the whole results. That's what they call the observer effect. The only reason they're observing it, the only reason there's an effect is because of the way they're observing it is putting in field sensors that take away from the magnetic interactions. So obviously when they shine light on it, they're infusing electrons, nothing more than these particles here. They're forcing them to go into that same interaction. They shouldn't do that. They should just take them when they come out into their CMOS. And now they are doing that. Originally they told me, no, you can't do that because it will destroy the CMOS. I said, no, we are doing it. We're doing it with a smartphone. And I went to the University of Geneva back at this time 6 years ago. I think it was 6 years ago, or maybe 5 or 6 years ago, in that area when nobody would listen to me. I said, well, I'll just go there, go to school there, which I did. And I took a course there for particle physics. I interacted with the professors, and I told them, I said, here's what we're doing. We're focusing our light through a venturi, and this is as simple as it gets, is a venturi. You see this? That's all it is. Now, what we did, though, we did it like this. So all of this was right coming through this way now. And we made it so tight that only the white could get through here. And the black had to bounce back out. The black stayed way out here. So that's how we did ours. And that created this right here. And it was so tight that only the white could get out. These are black all over here. There's black ones all over, and they can't get through. And then they come right back in over here. That's exactly how it works with the venturi. Fission, fusion, raw energy. I think we can get free energy. I see no reason why not. Okay, now, I'm going to be honest with you. I went to the University of Geneva for particle physics online, and I interacted with them, as I probably already mentioned, and I told them that we were focusing, and we were using CMOS, and we could see the particles. I sent them all the information, how to focus and so forth, and using a venturi. Now, they're using protons, which are much, much bigger. So, but that's what they want to stay in that realm. That's why they didn't take any big attention to what I was showing them. But what I was showing them is what they want to see. So what happened, this was 5, 6 years ago. And what happened is over the last few years, which is like, I think 2019 or so, they shut down, 2018, they shut down the Large Hadron Collider to upgrade it, to do exactly what I was telling. Now, whether I had anything to do with it, I have no idea. But over the past few years, far from sitting idle, the LHC has been a buzz of activity. They started to upgrade the collider's capabilities to prove its luminosity. That's the focus, which is essentially a measure of how many particle collisions there are likely to be in a square centimeter per second. That's how they ended up focusing. It's just like I said. Then they also have boosted their detectors using CMOS. Precisely the same thing that I mentioned. And now it's back online, and it's doing exactly what they expected, much more powerful. It just came back online to April 2022. And the new powerful collider could spur breakthroughs in the hunt for physics beyond the standard model. Well, I've already spurred those breakthroughs, and they're already done, but they need to be authenticated by these major players. Okay, this was 7 years ago. They took a vacuum chamber up into space, which is basically zero gravity. It's very low gravity, but not zero. Now, and they injected these charged particles of dust to see, and they figured they would see them all line up as like this and go this way and be like almost like a square cube of lattices. However, this is what happened. Now, I'm going to let this play. These are the micron-sized dust particles. They're allowed in, and they are charged. They have an extra electron on them. Now, I'm going to go way slow so you can see something that most people are going to miss. Now, watch this. All right, here comes these particles. Watch them start to line up in a line because they're pushing other ones away. You stay away from me, I'll stay away from you. So they form these actual lines of charged particles pushing against each other, but keeping a dark space in between each other. All right, now it's starting to form. The dark particles are starting to be pushed to the center. And eventually, they will go woof, 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 and all of the black ones, well, the dark sides of the particles, and I showed you they can separate, and in space, they appear to separate. If there's extra charged particles, extra electron shower particles, which there will be. From the sun, you're going to have all of these separated. You're going to have just white ones, you can have some just black ones, you can have chunks of white, chunks of black, chunks of both together. You're going to have all kinds of things coming off the sun. So, we have to assume that we will have these kind of swirls coming off the sun of all these different charged particles. Now, as they settle, they push the dark matter into the center. Watch what happens. There is a little bit of gravity. You can see a little bit of gravity going down towards the Earth. But not enough it makes it like an oblong hole in the center instead of a perfectly round black hole, which you would find out in the middle of space. It would be perfectly round because there'd be no attraction. Well, it depends on how close it was to other bodies. But here's what they observed. They were hoping to see this lattice shape come up. And that is not what they saw. Here's what happened. Look at this. Boom. Watch here. Watch it bounce up and down, bouncing up and down, up and down, up and down, up and down. Why is it bouncing up and down? Why isn't it just going up and staying up? Why is it coming back down? I can tell you why. The bucket is out here. It's pushing these up. They're banging into the bucket, and they're bouncing back down. Same thing here. Bounce back, and they're all the time they're pushing the excess dark matter into the center because there's more dark matter than there is white. Basically, it's as simple as that. Look, see it bounce, 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 and eventually it will just make a total, complete crust around here, and then these will be tightly held, and then they will push away at all the rest of them, so they'll end up having a less and less atmosphere, just like the Earth does. I think the center of our Earth is dark matter. Now listen to this. During the experiment, they contacted the Earth guys. They had no clue this was going to happen. Absolutely blown away. One guy from Max Planck freaked out. Now, I wasn't really involved in this, although I did communicate to the Russians and to Fermilab about this. And because I understand what's going on. One of the guys at Max Planck Institute locked himself in his office for like 3 weeks, they said, because he just freaked out. He just had no idea what to do. It goes against every single thing they've been taught. Every single thing they've been taught. He locked himself in his office for several weeks. Okay, as they say at Fermilab, that is the one that just pushes everything down. It's a fixed particle. That one there burns everything. I agree with that 100%. And here is the proof of it right now in this atomcentral.com video showing an atomic bomb blast. I am going to turn this down to a slower speed, which will make it so that we can see it more clearly. What we're going to see is this house. The first thing that's going to happen is the white particles from the atomic bomb blast will hit, because they coat the dark matter. I showed you the dark matter will always go to the center, and the outside will be the white matter. That's why we've never seen the dark matter. The only time you saw it was when I showed it to you on showing the dark particles on top of the white particles. Otherwise, you never see it. They don't emit, they don't absorb, they don't reflect. They will interfere with light coming from behind it, but that's it. And normally, the light coming from behind it, the dark is encapsulated in the middle, so that's why nobody's ever seen it before. It's part of everything, it's just that it's inside of everything. So nobody's ever seen it. It's dark. They're right about that. So here goes, Teapot Apple 2. Boom. Atomic bomb goes off. What happens? The house burns. Just burns. That's all you're seeing. I just stopped it. It didn't move. Nothing moved. It's just all nothing but burning. And watch what happens next. The dark matter comes. Boom. That's when it goes. Now what's going to happen next? Everything's going to come back, because you have a void in space, basically, and everything will turn around and come back. Alright, so I think I've made my case quite strongly, and I'm hoping for somebody like David to come along and work with us at Mudfossil University in every field of science, every field, because they all have to be reviewed. All right, thank you.